The core maths for Maclaurin series. I've got the June 2024 FP2 international paper. Question 7 says, given that y is equal to e to the x sine x, we've got to show that the sixth derivative is something times the second one, and you've got to work out what that k is, and then determine the first 5 non-zero terms. The sixth derivative, right? So here we go. So I'm going to work out the 6 derivatives. Take a big deep breath. Right, so we're going to do y by dx to start off with. You need to use the product rule. Differentiate the e to the x, just e to the x. So it's e to the x sine x, and then when we differentiate the sine x, we get cos x. Can't do much with that, so I'll leave it like that. Second derivative. Now, I've already differentiated e to the x sine x and got that. So that's still going to be the same. When I differentiate the e to the x cos x, though, it'll still be I have the e to the x cos x, differentiate the e to the x. Cos x becomes minus sine x, so it looks like this. This simplifies down a little bit, though, because these two terms go, and I've got 2 e to the x cos x. Then the third derivative, product rule again. So differentiate the e to the x, I get that. Differentiate the cos x, I get minus sine x. Can't do much with that. I suppose I could take out like a factor, but I don't think it makes my life much easier, to be honest. Then the fourth derivative, differentiate this, differentiate the e to the x, cos x becomes minus sine x. This one, I'll have minus 2 e to the x sine x, and then minus 2 e to the x cos x. And the cos x terms go this time, so I'm left with minus 4 e to the x sine x, which is equal to minus 4y, which is handy because I know what I know how to differentiate y because I've just done it before. Then the fifth derivative, well, I'm just differentiating this, so it's minus 4 times dy by dx. The sixth, well, I've really got to differentiate this twice, so it's like the second minus 4 times the second derivative. Or I could say, well, it's this differentiated again, so it's minus 4 times that differentiated, minus 4 d2y over dx squared. So the k is minus 4, and there we go. So we've shown that the sixth derivative is minus 4 times the second derivative. Now, if we're going to do the Maclaurin series, I need what the values of these are when x is equal to 0. Putting 0 into this one, let's get 0 because the sine of 0 is 0. This one, that term's going to go, but cos x is 1, so that's going to be 1. This one is going to be 2 because e to the naught and cos of naught are both 1. That term goes, so that's going to be 2 as well. Then I've got minus 4y. Well, I've already done y, and I've got 0, so minus 4 lots of 0 is 0. And then I want minus 4 times dy by dx. Done dy by dx, that's equal to 1, so that's minus 4. And then minus 4 times the second derivative, it gives me minus 8. So those are all my sort of values of all the derivatives when x is 0. And I've actually got 1, 2, 3, 4, 5 non-zero ones, so that's good. So the Maclaurin expansion, this is what it says in the formula book. But annoyingly, right, in terms of y, I don't know why they do that, not necessary. But the y version kind of looks like this, really. So y when x is 0, and then dy by dx is the f dash, really, when x is 0, and the second derivative when x is 0, and so on. So that's but we don't really need to do that. We're just going to use that formula because we're f of naught is when y is equal to 0, when x is 0. So that's naught, and then we've got x times 1, and we've got x squared over 2 factorial times 2, and x cubed over 3 factorial times 2 again, and x to the 4, it's going to be multiplied by this one, that's multiplied by 0. Then we'll x to the 5 over 5 factorial times minus 4, and finally x to the 6 over 6 factorial times minus 8. And if we simplify that down, I like to have the coefficients in front rather than have the x's over the 3. And that's the Maclaurin series.